In this video, we will discuss about PN junction diode and its characteristics, which are useful for first year students, first year BTech engineering students. Before discussing the PN junction diode and its characteristics, we need to have some basic knowledge of semiconductors and electronic devices. Okay. Yeah, electronics is the branch of engineering which deals with current conduction through a vacuum or gas or a semiconductor. An electronic device is that which current flows through a vacuum or gas or semiconductor. Valence electrons. The electrons in the outermost orbital of an atom are known as valence electrons. The maximum number of valence electrons can be 8. These valence electrons determines the electrical property of material. Free electrons. The valence electrons, which are very loosely attached to the nucleus, are known as free electrons. On the basis of electrical conductivity, materials are generally classified into conductors, insulators, and semiconductors. Conductors. When the number of valence electrons of an atom is less than 4, the material is usually a metal and a conductor. A conductor is a substance which has large number of free electrons, that is 10 power 28 free electrons. Examples are iron, copper, and aluminum. Insulators. When the number of valence electrons of an atom is more than 4, the material is usually a non-metal and an insulator. An insulator is a substance which has practically no free electrons at ordinary temperature, that is 10 power 8 free electrons. Examples are diamond, wood, sulfur, and neon. Semiconductors. When the number of valence electrons of an atom is 4, the material has both metal and non-metal properties and is usually a semiconductor. A semiconductor is a substance which has very few electrons at room temperature. A semiconductor is a substance which has a resistivity of 10 power minus 4 to 0.5 ohm meters in between conductors and insulators. Examples are germanium, silicon, selenium, carbon. Semiconductors are used in making electronic devices because the flow of electrons can be controlled by semiconductors. Types of semiconductors. There are two types of semiconductors: intrinsic semiconductor, extrinsic semiconductor. Intrinsic semiconductor. A semiconductor in an extremely pure form is known as intrinsic semiconductor. In an intrinsic semiconductor, even at room temperature, whole electron pairs are created. When electric field is applied across an intrinsic semiconductor, the current conduction takes place by two processes, namely by free electrons and holes, as shown in figure. Now, figure consists of an intrinsic semiconductor which is connected to a battery. Holes being positively charged move towards the negative terminal of supply. As the holes reach the negative terminal of B, electrons enters the semiconductor crystal near the terminal and combine with holes, thus cancelling them. At the same time, the loosely held electrons near the positive terminals A attracted by from their atoms into the positive terminal. This creates new holes near the positive terminals, which is again drift towards the negative terminal. Extrinsic semiconductor. This is achieved by adding a small amount of suitable impurity to a semiconductor. It is then called impurity or extrinsic semiconductor. The process of adding impurities to a semiconductor is known as doping. The amount and type of such impurities have to be closely controlled during the preparation of extrinsic semiconductor. Generally, for 10 power 8 atoms of semiconductor, one impurity atom is added. Depending upon the type of impurity added, extrinsic semiconductors are classified into N-type semiconductor and P-type semiconductor. N-type semiconductor. When a small amount of pentavalent impurity is added to a pure semiconductor, it is known as N-type semiconductor. The addition of pentavalent impurities provides a large number of free electrons in a semiconductor crystal. Examples are arsenic and antimony. Arsenic is atomic number of 33, whereas antimony is atomic number of 51. Such impurities which produce n-type semiconductors are known as donor impurities because they donate or provide free electron to the semiconductor crystal. Arsenic is a pentavalent, that is, its atoms have 5 valence electrons. An arsenic atom fits in the germanium crystal in such a way that its 4 valence electrons form covalent bonds with 4 germanium atoms. Figure shows a free electron. Why? Because due to arsenic, it is having a pentavalent impurity. 4 electrons are having covalent bond with 4 germanium atoms. Remaining 1 electron will become as a free electron. Fifth valence electron of arsenic atom finds no place in covalent bonds and is thus free as shown in figure. Therefore, for each arsenic atom added, 1 free electron will be available in the germanium crystal. Though each arsenic atom provides 1 free electron, an extremely small amount of arsenic impurity provides enough atoms to supply millions of free electrons. It is called n-type semiconductor. P-type semiconductor. When a small amount of trivalent impurity is added to a pure semiconductor, it is called p-type semiconductor. The addition of trivalent impurities provides large number of holes in the semiconductor. Examples are gallium, atomic number 31, and indium, atomic number 49. Such impurities which produce p-type semiconductors are known as acceptor impurities because the holes created can accept the electrons. When a small amount of trivalent impurity like gallium is added to germanium crystal, gallium is a trivalent, that is, its atom has 3 valence electrons. Each atom of gallium fits into the germanium crystal, but now only 3 covalent bonds can be formed. It is because 3 valence electrons of gallium atom can form 3 single covalent bonds with 3 germanium atoms, as shown in figure. The fourth bond is incomplete, being short of 1 electron. This missing electron is called hole, as shown in figure. Therefore, for each gallium atom added, 1 hole is created. A small amount of gallium provides millions of holes. p-n junction. When a p-type semiconductor is suitably joined to n-type semiconductor, the contact surface is called p-n junction. p-n junction is fabricated by special techniques. One common method of making p-n junction is called alloying. At the instant of p-n junction formation, the free electrons near the junction in the n region begins to diffuse across the junction into the p region, where they combine with holes near the junction. The result in the n region loss free electrons as they diffuse into the junction. This creates a layer of positive charges, pentavalent ions, near the junction. As the electrons move across the junction, the p region loses holes as the electrons and holes combine, which is as shown in figure. The holes are the majority carriers in p-type material and electrons are the majority carriers in n-type material. In p-type material, minority charge carriers are electrons, which are depicted with dot, whereas n-type material holes are the minority charge carriers. Now in the middle, ions are formed, which forms a depletion layer, as shown in figure. The result is that there is a layer of negative charges, trivalent ions, near the junction. These two layers of positive and negative charges form the depletion region. The positive and negatively charged set up an electric field. This is shown by a black arrow, as shown in figure. The electric field is a barrier to the free electrons in the n region, there exists a potential difference across the depletion layer and is called barrier potential. The barrier potential of p-n junction depends upon the type of semiconductor. For silicon, it is 0.7 volts. For germanium, it is 0.3 volts. Forward biasing. When external DC voltage applied to the junction is in such a direction that it cancels the potential barrier, thus permitting current flow, it is called forward bias. To apply forward bias, connect positive terminal of the battery to a p-type and negative terminal to n-type as shown in figure. When p is connected to positive, holes are repelled, and n is connected to negative, electrons are repelled in the n-type material, which causes the width of the depletion layer is thin. The applied forward potential establishes an electric field which acts against the field due to potential barrier. A small forward voltage is sufficient to completely eliminate the barrier. Once the potential barrier is eliminated by the forward voltage, junction resistance becomes almost zero, and a low resistance path is established for the entire circuit. Therefore, current flows in the circuit. This is called forward current. From the forward characteristics, it has been seen that the first region OA, the current increases very slowly and the curve is non-linear. It is because the external applied voltage is used upon in overcoming the potential barrier. However, once the external voltage exceeds the potential barrier voltage, the p-n junction behaves like an ordinary conductor. Therefore, the current rises very sharply with increase in external voltage region AB on the curve. The curve is almost a linear, which is as shown in figure. Voltage is in volts, forward current is in milliamperes. Reverse biasing. When the external DC voltage applied to the junction is in such a direction that potential barrier is increased, it is called reverse biasing. To apply reverse biasing, connect negative terminal of the battery to p-type and positive terminal to n-type as shown in figure. It is clear that the applied reverse voltage establishes an electric field which acts in the same direction as the field due to potential barrier. Therefore, the resulting field at the junction is strengthened and the barrier height is increased as shown in figure. The increased potential barrier prevents the flow of charge carriers across the junction. Thus, a high resistance path is established for the entire circuit and hence current does not flow. Figure shows a negative terminal is connected to p-type and positive is connected to n-type material. Obviously, holes in the p-type material is attracted by the negative terminal and electrons in the n-type material is attracted by the positive terminal. Due to that, without depletion area increases. However, in practice, a small current of order of microamperes flows in the circuit with reverse bias as shown in figure. The reverse characteristics. This is called to reverse saturation current and is due to the minority charge carriers. It may be recalled that there are a few free electrons in p-type material and few holes in n-type material. These undesirable free electrons in p-type and holes in n-type material are called minority carriers. If the reverse voltage is increased continuously, the kinetic energy of electrons may become high enough to knock out the electrons and the semiconductor atoms. At this stage, breakdown of junction occurs. Important terms. Breakdown voltage. It is the minimum reverse voltage at which p-n junction breaks down with sudden rise in reverse current. Knee voltage. It is the forward voltage at which the current through the junction starts to increase rapidly. Semiconductor. A p-n junction is known as a semiconductor or crystal diode. Diode is defined as two-terminal electronic component that only conducts current in only one direction. An ideal diode will have zero resistance in one direction and infinite resistance in reverse direction. The basic structure and the symbol is as shown in figure. A crystal diode has two terminals. If arrowhead of a diode symbol is positive with respect to the bar of the symbol, the diode is forward bias. If the arrowhead of the diode symbol is negative with respect to the bar, the diode is reverse bias. Diode applications in rectifiers, voltage regulators, clipping circuits, clamping circuits, comparators, and switch. Diode current equation. The current flowing through the diode is given by ID equals to I naught into e power V by eta Vt minus 1, where V is the applied voltage, I naught is the reverse saturation current in microamperes, T is the absolute temperature of PN junction in kelvins, where and K is the Boltzmann constant, which is equals to 1.38 into 10 power minus 23 joules per Kelvin. Q is the electric charge, 1.6 into 10 power minus 19 coulombs. Vt is the thermal voltage or voltage equivalent, which is equals to Kt by Q. By substituting the values of Boltzmann constant and charge, the value of Vt equals to T by 11,600, where T is the ultimate temperature. Eta is the empirical constant depending on the type of the semiconductor. Its value is 1 for germanium and 2 for silicon. Diode resistance. Forward resistance. The resistance offered by a diode to a forward bias is called forward resistance. This resistance is of two types: DC forward resistance and AC forward resistance. DC forward resistance or static resistance. It is measured by the ratio of DC voltage across the diode to the resulting DC current through it. In figure, it is clear that when the forward voltage is OA, the forward current is OB. Therefore, DC forward resistance equals to OA by OB. AC forward resistance or dynamic resistance. It is opposition offered by the diode to the changing forward current. It is measured by the ratio of change in voltage across the diode to the change in current through it. AC forward resistance RF equals to change in voltage across the diode by change in current through the diode. Corresponding change in current through the diode. For forward voltage OA, circuit current is OD. For forward current OC, the circuit current is OF. Therefore, AC forward resistance equals to RF equals change in forward voltage by change in forward current. Change in forward voltage is OC minus OA, which is equals to AC, whereas change in forward current is OF minus OD, which is equals to DF. The characteristics are as shown in figure below. Transition capacitance. Just like capacitors, a reverse bias PN junction diode is also stores electric charge at the depletion region. The depletion region is made up of immobile positive and negative ions. In depletion region, the electric charges do not move from one place to another place. However, they expert electric field or electric force. Therefore, charge is stored at the depletion region in the form of electric field. The ability of the material to store electric charge is called capacitance. Thus, there exists a capacitance at the depletion region, otherwise called space charge or barrier or depletion region capacitance. CT is given by CT. CT equals to dq by dt. The change in capacitance at a depletion region can be defined as a change in electric field, electric charge per change in voltage dq by dV, where Ct is transition capacitance, dq is change in electric charge, dV is change in voltage. The transition capacitance can be mathematically written as Ct equals to epsilon A by W, where epsilon is the permittivity of the semiconductor, A is the area of the plates are p-type or n-type regions, and W is the width of the depletion region. Diffusion capacitance. Diffusion capacitance occur in a forward bias p-n junction diode. Diffusion capacitance is also sometimes referred as storage capacitance. It is denoted as CD. Diffusion capacitance CD. The diffusion capacitance occurs due to the stored charges of minority electrons. Diffusion capacitance is directly proportional to the electric current or applied voltage. Electric current or applied voltage. If large electric current flows through the diode, a large amount of charge is accumulated near the depletion region. The formula for diffusion capacitance is CD equals to dq by dV, where CD is diffusion capacitance, dq is the charge change in number of minority carriers stored outside the depletion region, dV is the change in voltage applied across the diode. Breakdown mechanisms. There are two types of breakdown mechanisms. One is avalanche breakdown. The minority carriers under reverse bias condition flowing through the junction acquires kinetic energy, which increases with the increase in reverse voltage. At a sufficient high reverse voltage, the kinetic energy of minority carriers becomes so large that they can knock out electrons from the covalent bonds of a semiconductor material. As a result of collision, the liberated electrons in turn liberate more electrons, and the current becomes very large, leading to the breakdown of the crystal structure itself. This phenomenon is called avalanche breakdown. The breakdown region is the knee of the characteristic curve. Now the current is not controlled by the junction voltage, but rather by the external circuit. Second one, Zenard breakdown. Under a very high reverse voltage, the depletion region expands and the potential barrier increases, leading to very high electric field across the junction. The electric field will break some of the covalent bonds of the semiconductor atoms, leading to a large number of free minority carriers, which suddenly increases the reverse current. This is called Zenard effect. The breakdown occurs at a particular and constant value of reverse voltage called the breakdown voltage. It is found that the Zenard breakdown occurs at electric field intensity above about 3 into 10 power 7 volts per meter. Figure shows the VI characteristics of a p-n junction diode. Forward voltage is in volts, forward current is in milliamperes, there is reverse voltage in volts, and reverse current is in microamperes. Zenard diode. Zenard diode symbol is as shown in figure. A Zenard diode is a silicon p-n junction diode that is designed for operation in the reverse breakdown region. The breakdown voltage of Zenard diode is set by carefully controlling the doping level during manufacture. When the reverse voltage reaches reverse breakdown, its voltage remains almost constant. Even the current changes drastically, and this is a key to Zenard diode operation. The Zenard diode characteristics are as shown in figure below. The Zenard diode VI characteristics are as shown in figure below. Vz is the breakdown voltage. Reverse breakdown region is normal. Zenard breakdown. Zenard diodes are designed to operate in reverse breakdown. The two types of reverse breakdown is Zenard breakdown and are avalanche and Zenard. The avalanche effects occur in both rectifier and Zenard diodes. It's sufficiently high reverse voltage. Zenard breakdown occurs in a Zenard diode at low reverse voltage. A Zenard diode is a heavily doped to reduce the breakdown voltage. This causes a very thin depletion region. As a result, an intense electric field exists within the depletion region near the Zener breakdown voltage. The field is intense enough to pull electrons from their valence bands and create current. Zener breakdown. Zener diodes with breakdown voltage less than approximately 5 volts operate predominantly in Zener breakdown. Breakdown voltage greater than approximately 5 volts operates predominantly in avalanche breakdown. However, both types are called Zener diodes. Zener diodes are commercially available with breakdown voltage from less than 1 volt to more than 250 volts with specified tolerance from 1% to 20%. Breakdown mechanisms. As the reverse voltage is increased, the reverse current remains extremely. As the reverse voltage VR is increased, the reverse current remains extremely small up to the knee of the curve. The reverse current is also called the Zener current IZ. At this point, the breakdown effect begins. The internal Zener resistance is called Zener impedance begins to decrease as the reverse current increases. As the reverse voltage is increased, the reverse current remains extremely small up to the knee of the curve. The reverse current is also called the Zener current. At this point, the breakdown effect begins. The internal Zener resistance is called Zener impedance begins to decrease as the reverse current increases rapidly. From the bottom of the knee, the Zener breakdown voltage remains essentially constant, although it increases slightly as the Zener current increases. The characteristics are as shown in figure. Zener knee current, Zener test current, and Zener maximum current as shown in figure. The ability to keep the reverse voltage across its terminal essentially constant to key feature of the Zener diode. That is the key feature of the Zener diode. A Zener diode operating in breakdown acts as a voltage regulator because it maintains a nearly constant voltage across its terminal over a specified range of reverse current values. A minimum value of reverse current must be maintained in order to keep the diode in breakdown for voltage regulation. When the reverse current is reduced below the knee value of the curve, the voltage decreases drastically and regulation is lost. Also, there is a maximum current above which the diode may be damaged due to excessive power dissipation. Basically, the Zener diode maintains a nearly constant voltage across its terminals for values of reverse current ranging from IZK to IZM. A nominal Zener voltage Vz is usually specified on the datasheet at a values of reverse current called Zener test current. Zener equivalent circuit. Ideal mode of Zener diode has a constant voltage equal drop equal to the nominal Zener diode. This constant voltage drop across the Zener diode produced by reverse breakdown is represented by a DC voltage symbol even though the Zener diode does not produce a voltage. It is as shown Thank you for watching. Please share and subscribe if it is useful.